Section 2.6 problems. First two questions are asking us to find domains of functions, two very different functions. If you notice, the first function is quadratic. It's called a polynomial function, and polynomial functions by definition are defined absolutely everywhere. These do not contain square roots. These do not contain denominators that could potentially be zero, and they don't have any issues whatsoever. So for problem number one, the domain is going to be all real numbers. That's how you say it in words. Well, all real numbers means every number on the x-axis, negative infinity to plus infinity. In other words, there's no number that you can't substitute in here for x and calculate the corresponding y coordinate. So the domain is all real numbers. This is not the case with problem 2. Problem 2, we have a function j of x, which has two potential problems. There's a square root, and we have to always be on guard for that. And we also have the square root appearing in the denominator, and denominators have issues when they're zero. So there's two things we have to worry about. First of all, the square root is only defined for positive values, so we have to look at what is underneath the square root must always be greater than or equal to 0. The square root of 0 is fine. The square root of a negative number is not fine. So let's first find those numbers right there. So that means 24 has to be greater than or equal to positive 3x, or 8 has to be greater than or equal to x. That would make the square root okay. So this makes the square root okay. But if x equals 8, we encounter another problem. If x equals 8, then we get in the denominator, well, the numerator would be 5 times 8, but the denominator would be the square root of 24 minus 3 times 8, and that would give us a 0 in the denominator, and that is no good. So x cannot be the value of 8. So we have two issues here. X must be smaller than 8, and separate issue, x cannot equal 8. Okay. So how do we quote this then? Draw a number line. There's 8, and we cannot have 8. But we can have anything smaller than 8. Now, just check that. Suppose we take a number like 9, which is larger than 8. If we substitute 9 here in the original, 24 minus 3 times 9 is 24 minus 27. See, that's a negative number in the square root. That's no good. So we are in the correct region here, in the correct interval to the left of 8. And we can't include 8. So we can say that in one interval. The allowable values of x are not including 8, parenthesis here, left forever. And that will make the function j of x completely defined as long as the values of x you pick are in that interval. So there's the domain for that particular problem. Let's take a look at problem number 3. Let f of x be the linear function x minus 5, and let our second function, g of x, be x squared minus 1. Let's add them, let's subtract them, let's multiply them, and then finally determine the domain after we have formed our new function here. Okay, so again, starting place is move from notation that doesn't help so much to notation that does. That simply means to take the two functions, write them down, and put a plus sign in between. So f of x is x minus 5, g of x is x squared minus 1, and this is our new function that's being created. If there are like terms here, we can add it together. Negative 5 and negative 1 make negative 6. Let's do a little rearrangement. Positive x squared plus x minus 6 is our new function created by taking f of x and adding it to g of x. So this is our new function, and this is what has been created. This is, again, polynomial. So the domain right away is all real numbers, negative infinity to plus infinity. There's no way that you cannot substitute a value of x in here and compute a corresponding y coordinate. So that's part A. Let's take a look at part B. Part B, we have to subtract the two functions, and it's f minus g. Subtraction, you have to be a little careful. F minus g of x is f of x minus g of x. So yes, you write down the function f of x. Yes, you write down the function g of x. Yes, you put a minus sign in between, but you have to subtract off the entire g of x function. So the parentheses there are mandatory. You need to have the parentheses there. Now distribute and then clean it up if there are any like terms, and you can rearrange it as well. Negative x squared plus x, negative 5 plus 1 is negative 4. So there is our new function. Again, it's polynomial, and the domain is, again, all real numbers, so negative infinity to plus infinity, and there's part B. What do we have for part C? Part C, we have the product of the two functions. Okay, f times g of x. So let's do part C. We want f times g evaluated at x. This means f of x times g of x. And yes, write down the function f of x. Yes, write down the function g of x and multiply them. But that means you must have parentheses around both quantities, or else it's not multiplying the entire function f by the entire function g. Good idea to multiply this out. X times x squared is x cubed. X times negative 1 is negative x. Negative 5 times x squared is negative 5x squared. And negative 5 times negative 1 is plus 5. Now, if you have any like terms, we can add them together. We don't. You could rearrange it, though. X cubed minus 5x squared minus x plus 5. Again, that's another polynomial, so the domain there is negative infinity to plus infinity, once again. Let's take a look at the next problem. Oh, composition. Given a linear function 5x plus 6 and another function g of x, 2x squared minus x minus 1, find each of the following. F compose g. Okay, so always the starting point. F compose g of x means f of g of x. Put the g of x function inside the f of x function. So if we look at f of x, 5x plus 6, literally it's going to be 5 times g of x plus 6. Now just replace g of x. What is g of x? Well, it's 2x squared minus x minus 1 plus 6. And if you wish, you can clean that up. Distribute the 5. 10x squared minus 5x minus 5. Don't forget the plus 6. And you can add some like terms there. 10x squared minus 5x plus 1. Okay, and we're not asked to find the domain. Here, again, it's a polynomial, so the domain would be all real numbers. Part B, that was part A. Part B, we're asked to find the composition in the other direction. So this was not done on the PowerPoint. So now we have a chance to do something different. So we'll come down here and take G compose F at x. That means G of f of x. This means we're putting the f of x function inside the g function. So go to the g function. The g function, here's our quadratic, 2x squared minus x minus 1, and replace the x by f of x. So it's 2 times f of x squared minus f of x minus 1. Now just put in what that function f of x is, and you'll have the composition. 2 times f of x is 5x plus 6 square minus the function f of x, 5x plus 6, and then minus 1. And we can work that out a little bit and simplify if we wish. We'd have to square this out right here, so we'll do that very quickly. 25x squared plus 60x plus 36, distribute the negative sign. We can then multiply through here. 50x squared minus 120x plus 72 minus 5x minus 6 minus 1. We can then add like terms. We can go on and simplify as much as we want. Let's take a look at what else we have to do here. Okay, this is different. Let's take a look at this one. This is finding f compose g, and then we have a negative 1 there. See, there's never any multiplication. This is function notation, and it means find f of g at negative 1. Remember, if this were an x, it would be f of g of x. So since x is now negative 1, it's f of g of negative 1. What I would do is first write the function g of x down. So let's drag that down here. 2x squared minus x minus 1. Let's find g of negative 1. Since we can do this and get a numerical value, why not do that? 2 times negative 1 squared minus negative 1 minus 1. Now we have to simplify this, because this number that we get for g of negative 1 will be substituted into the function f. So this would be 2 times 1 plus 1 minus 1. That looks like 2. Okay, so to write f of g of negative 1 and having computed g of negative 1 to be 2, all we got to do now is find f of 2. So write your f function down. F of x was 5x plus 6. Finding f of 2 is now pretty simple to do. Replace x by 2. 5 times 2 plus 6, so 10 plus 6 is 16. We could form the composition and then substitute a negative 1, but it's far easier if you have a numerical value for x to first compute this and get that numerical value, and then substitute that numerical value into the other function. Makes the math a lot easier. Let's see what else we have left to do. Problem 5. Given the rational function f of x, 4 divided by x plus 2, and the rational function g of x, 1 over x, find each of the following. Okay. So in the PowerPoint slide, we did f compose g of x. And we did the domain as well. Let's make a small change then, and let's do g compose f at x. This way would be a little bit different than the PowerPoint. So the better notation means g of f of x. Okay, that means we're going to put the f of x function into the g of x function. So g of f of x, since g is 1 over x, it's now 1 over f of x. Okay. So that's 1 divided by, what's the f of x function? It's 4 divided by x plus 2. Okay. And 1 divided by a fraction means to take the reciprocal. So 1 divided by 4 divided by x plus 2 means x plus 2 over 4. So this is a new function created by, in this case, not doing f of g, but making a change, doing g compose f, putting f inside g, and now we've attained an entirely new function. You see that the composition is very different. It does depend upon whether you put g inside f or f inside g. The results are very drastically different. Let's carry on with this then and find the domain. So let's get the domain of g compose f. Okay, so that would be for this one that we just did. Okay, Well, this is a linear function. You could write this as 1/4 x plus 2/4 if you want, but you don't need to do that. There are no square roots here, so we don't have to worry about that. And there is a denominator, but it's a number in the denominator. It can never be 0. There's no x in the bottom. So this function here is going to be defined for all values of x, which is -infinity to +infinity as an interval. Is there something more to do? Yes, there's one more problem that we can do. Okay, this is the one that we did on the PowerPoint slide. This is pulling apart the function h, which is x squared plus 5, as a composition of two problems. So let's make a change. Let's say h of x is the function 2x plus 3 to the 4th power. That function, there's actually two there that make up the function h. There's the function that does the 4th powering, and then there's the function being raised to the 4th power. Those are your two individual functions. So we'll let, let's say, f of x be the one doing the powering, x to the 4th, where the g of x function is the function being raised to that power. That's the 2x plus 3. And you can see, if you take g of x and put it inside there, replace that x, replace this x here by the entire g of x function, you will get h of x, which means that h of x is found by putting the g function inside the f function. So it's f of g, or in the other notation, it's f composed g of x, like that. That concludes section 2.6 problems.